Some of the universe's biggest questions regarding dark matter, antimatter and cosmic rays could soon be answered by a mission that launched here from the Kennedy Space Center on board Space Shuttle Endeavour. The Alpha Magnetic Spectrometer, or AMS, will become a permanent long-term experiment on the International Space Station. 56 institutes from 16 countries have come together to build the AMS. It weighs nearly 7,000 kilograms, measures approximately 3 by 3 by 5 metres, and at 16 years in the making, cost in the region of $2 billion. The experiment arrived at the Kennedy Space Center in August 2010 and was mounted inside Endeavour in March 2011, finally launching on the 16th of May.
Well, I'm the commander of STS-134. We've got a whole list of mission objectives, probably 30 things on the list. But the big objectives is to get the Alpha Magnetic Spectrometer installed on the outside of the space station.
In my mind, this is like the Hubble Space Telescope. I mean, it has the same type of potential for revolutionizing our understanding of the universe.
The AMS will use a large magnet to create a field with a strength 3,000 times stronger than Earth's magnetic field to bend the path of charged cosmic particles as they travel through space. 8 different instruments on the AMS will provide information about those particles as they travel through the magnet, providing data that may help scientists determine just what the universe is made up of and how it began. We know that visible matter, like stars and galaxies, count for a tiny fraction of visible matter in the universe. The rest, around 95%, is only inferred. Dark energy is apparently causing the expansion of the universe to accelerate, whilst dark matter is inferred to explain gravitational effects on galaxies, and has been used to explain the universe's so-called missing mass. Otherwise, galaxy clusters would lack the mass to stay together and would have moved apart by now. One candidate for dark matter particles is the theoretical neutralino particle. If they exist, their collisions could create excesses of electrons and anti-electrons, or positrons, that could be detected by the AMS. Antimatter, identical to regular matter but with opposite electric and magnetic properties, is also on the hit list for the AMS. The Big Bang theory for the formation of our universe assumes there was equal amounts of matter and antimatter present when the universe began, in the form of helium antinuclei or heavier elements that have never been found. The AMS will operate for some 10 years, and during that time it has the potential to detect these heavy particles, if they exist.
These particles carry charge. Because it carries a charge, it must have a mass. Because it has a mass, it's absorbed in Earth's atmosphere. And therefore you have to go to space.
The AMS was delivered by Space Shuttle Endeavour's final flight to the International Space Station, but particle physicists will be reaping the rewards from that experiment for many years to come. At the Kennedy Space Center, Baldwin for Astronomy Now.